Hi, I'm Ayngaran from Cambridge. Thank you for coming to watch my talk, and thank you to the organisers of Cosmology from Home for inviting me to speak at this nice virtual conference. So for this talk, I'll be talking about how we can use tools from the recent cosmological bootstrap program to construct all tree-level graviton bispectra to all orders and derivatives in the effective field theory of inflation. This is based on the work from an upcoming paper written with my great collaborators Giovanni Cabas, David Stefanisian, and Jakob Supel. If you're interested in learning more about the field of cosmological bootstrap, I encourage you to watch the talks of Harry, Gordon, and Dong Gang. So firstly, I will start by giving a quick primer on bootstrapping graviton bispectra. Then I'll review the effective field theory of inflation and discuss the building blocks of the operators which contribute to the graviton bispectra in the EFT of inflation. I will then discuss how we can use bootstrap tools to construct all tree-level graviton bispectra in the effective field theory of inflation. Finally, I will conclude with future directions for this work. So let's start with discussing how we can bootstrap graviton bispectra. In cosmology, we aim to measure correlation functions through the CMB and LSS, which can be traced back to the boundary at conformal time E0 from the end of inflation, which is believed to be a de Sitter-like expansion. In the cosmological bootstrap program, a helpful object to work with to compute these cosmological correlators is called the wavefunction of the universe. Thus, for the purposes of cosmology, we are doing quantum field theory in de Sitter for a generic field phi evaluated at conformal time E0, for which we can express the wave function as the path integral given by equation 1, where for spinning fields, indices are suppressed. For the path integral, we impose the boundary conditions that the field in the infinite past started from a Bunch-Davies vacuum and then takes on a value phi bar at conformal time E0. Like the wave function of any system, the wave function of the universe contains all the information of our universe. And for a spin-2 field gamma, we can parameterize it as equation 2, where gamma h is the spin h Fourier mode of the graviton with helicity h is equal to plus or minus 2. Note that we don't include the momentum conserving delta function in these expressions, which comes from translation invariance. So we do a saddle point approximation of the path to integral and then compute the wave function of coefficient psi n at tree level in perturbation theory, so contact and exchange Feynman diagrams. We denote the wave function coefficients as psi n, which have an implicit helicity dependence and then correspond to the usual cosmological correlators Bn. For example, we hope to use the CMB to see tensor modes soon, and from this measure the graviton bispectrum, which is related to the 3-point wave function coefficient psi3, as shown in equation 3. From equation 4 here, we can see that we can write a general 3-point wave function coefficient psi3 in terms of a polarization factor multiplied by a trimmed wave function coefficient psi3 trimmed, which is an SO3 scalar and can be computed from bulk time integrals. Here, we define the total number of spatial momenta contracted with polarization factors as alpha is equal to alpha1 plus alpha2 plus alpha3, and index contractions between the momenta and polarization tensors are left implicit. There can also be additional spatial momenta, but they are contracted amongst themselves. The polarization tensors, Eij, have the usual properties of being transverse, tracer, symmetric, etc. In order to construct an SO3 invariant object, we need to contract momenta with one of the red or blue tensor structures in equation 5, where the presence of a Levi-Civita tensor in the blue colored tensor structures tells us that the resulting graviton bispectrum will violate parity, so parity odd. All remaining contractions are made with delta ij's, and we generally omit the dependence of polarization tensors on momenta for simplicity of notation. We can see that alpha can be at most parity 6 in parity even case, with all 6 polarization indices contract from momenta and 7 in the parity odd case, since we can have at most 2 spatial momenta contracted with Levi-Civita tensor due to momentum conservation. We will deal with the parity even and parity odd cases separately. An important previous result is that of Maldacen and Pimentel from 2011, where assuming invariance under the full isometry group of de Sitter, so SO4, 1, in 4 dimensions, it was shown that for gravitons, only 3 cubic cosmological wave function coefficients are allowed, and of those, only the 2 parity even ones can lead to a non-vanishing bispectrum. But de Sitter boosts are actually broken in most phenomenologically relevant models of inflation. In the EFT inflation, the time diffeomorphisms are broken by a single scalar field that acquires a time-dependent VEV. The EFT inflation thus encapsulates a large class of single-field inflationary models. De Sitter with arbitrary breaking of boost, so the ISO3 group with dilations are the observed symmetries in the sky of statistical homogeneity, isotropy, and scalar invariance. For these isometries, Cumbersome in 2021 used the constraints of unitarity and locality to bootstrap all tree-level Graviton Bispectra to any orders in derivatives, and found that in the case of arbitrarily broken boosts, there were infinitely many parity even shapes and only 3 parity odd shapes that were consistent with unitarity and locality. For more details regarding these unitarity and locality constraints, I encourage you to watch Harry's and Gordon's talks. Of the 3 parity odd shapes, only 1 belongs to the effective field theory of inflation. Hence, we can now ask whether we can further constrain the parity even Graviton Bispectra to identify those that belong to the EFT of inflation. And the answer is yes. So I'll now briefly review the EFT of inflation from a Lagrangian or bulk perspective and categorize the operators which contribute to the Graviton Bispectra in the EFT of inflation. Starting with the usual ADM formalism, we work in unitary or Mauthausen gauge, where the gauge is fixed completely by taking the graviton to be transverse and traceless. Since we're interested in graviton interactions, we set the curvature perturbation theta to 0, which through the constraint equations sets the lapse variable to be 1 and the shift to be 0 at cubic order in gamma. This gives us the line element given in equation 6, where A is the scale factor and we define the Hubble parameter in the usual way of A dot over A. For now, we work in cosmological time, but later on we will convert to conformal time, which is more suitable for computing late-time cosmological correlators. In this gauge, the most general action that we can write down is one consistent with spatial diffeomorphisms, as given by equation 7. For our purposes, however, there are simplifications we can make. All time dependence will be fixed by scale invariance, since we are working in the scale invariant approximation, i.e. we assume h and its time derivative to vary slowly and restrict all time dependence to be that coming from the metric. In practice, this means that we work with a fixed de-Sitter background, so all correlators we compute are valid up to small slow roll corrections. The extrinsic curvature of constant time hypersurfaces for our metric is given by k mu nu, with non-zero components kij. We work with a perturbed extrinsic curvature defined by delta k mu nu. Only the 3-dimensional Riemann tensor is independent of the extrinsic curvature. We can then use the fact that the Weyl tensor is identically 0 in 3 dimensions, so the 3-dimensional Riemann tensor is completely determined by the 3-dimensional Ricci tensor. We can also use only the spatial components of delta k mu nu without loss of generality. Finally, we can make the redundancy of any cubic graviton operators containing the 3-dimensional Ricci tensor manifest with field redefinitions. The most general action is therefore given by equation 8, where we have separated out SEH, which includes the Einstein-Hilbert action, plus the terms required to make the unperturbed metric a consistent solution. This part of the action describes the minimal setup of slow roll inflation, with all other operators describing higher derivative corrections. Therefore, to compute the bispectral gravitons, we only need to consider EFT of inflation actions constructed out the extrinsic curvature delta Kij. This is actually the first time it's been shown that the quadratic and cubic action for massless gravitons that appears in addition to the Einstein-Hilbert part can be derived by considering covariant operators constructed out of the extrinsic curvature alone. This could also have repercussions for scalar non-Gaussianities. Note that we have not included any terms that depend on the trace of the extrinsic curvature, since this object vanishes to all orders in gamma. Therefore, we only need to consider operators which are quadratic and cubic in the extrinsic curvature. Hence, the most general action that contribute to the Graviton Bispectra at tree level is given by equation 9, where the operator OI are derivative of operators constructed out of covariant derivatives. And we've integrated by parts to move all derivatives onto a single extrinsic curvature building block delta Kij. Blue type 1 operators are quadratic in delta Kij and contribute to the quadratic action, which at tree level and to leading order in the field theory couplings is a single exchange diagram that perturbatively accounts for possible corrections to the graviton power spectrum. For the exchange diagram drawn below, the leading order contribution comes from taking the cubic vertex to be that of GR and the blue quadratic vertex coming from expanding 2 building block operators to quadratic order. There are also contact diagrams which contribute to the cubic wave function coefficient of gravitons. At this order, this exchange diagram is of a comparable size to the contact diagram that comes from these two building block operators, and indeed cancellations are required between these two diagrams for the EFT inflation consistency relations to be satisfied, and we've checked this explicitly. For the red type 2 bispectra, only contact diagrams contribute since there are no corrections to the quadratic action. For the final part of this talk, I'll focus on how we can bootstrap the type 2 graviton bispectra, since these can give phenomenologically larger signals than type 1 and are therefore of more interest for observations. Type 2 operators are constructed from 3 powers of the extrinsic curvature delta Kij, so we only need to write delta Kij to linear order in gamma, as shown in equation 10. Therefore, it follows that all graviton bispectra arising from type 2 operators contain an overall factor of K1, K2, K3 all squared. Remember that we can express a general 3-point wave function coefficient psi3 in terms of a polarization factor multiplied by a trimmed wave function coefficient psi3 trimmed. We rewrite the polarization tensors in terms of spinor helicity variables and encapsulate the contraction of the momentum with the polarization tensors in terms of a polynomial H alpha, whilst we deal with the scalar part of the wave function coefficient separately, as shown in equation 11. As mentioned previously, the trim wave function comes from time evolution in the bulk and can be computed from bulk time integrals. But instead of doing countless time integrals, we efficiently bootstrap them. To do this, we start with the fact that wave function coefficients and correlators at tree level are rational functions. We then use the fact that in general, wave function coefficients psi n scale as k cubed as a consequence of scalar invariance. And hence we can see that psi3 trimmed must have dimensions of k to the 3 minus alpha, given that the spinor helicity variable is dimensionless. Therefore, an initial ansatz we can write for the trimmed wave function coefficient is given by equation 12, where alpha is a total number of spatial momenta contracted with polarization factors, and f is a rational function of the free energies with appropriate dimensions. For massless gravitons, we have a bootstrap tool called the manifestly local test to constrain trimmed wave function coefficients, which are consistent with no inverse Laplacians in the action, as shown by equation 13. Now, the trimmed wave function coefficient can be a rational function of the free energies, and thus can contain a log divergence in minus e to naught at kt, and also contain poles at e to naught equals 0 of at most cubic degree, where kt is equal to k1 plus k2 plus k3. However, in our EFT of inflation operators, there are too many derivatives for log divergences to arise, and the fact that each gamma is differentiated at least once is enough to rule out e to naught equals naught poles in the wave function. For our interest, we can therefore restrict the trimmed wave function coefficient to be a rational function with poles only occurring when k1 plus k2 plus k3 equals 0, as shown in equation 14, where p is a polynomial of degree p minus 3 minus alpha, symmetric in the free energies. Due to the prefactor of k1, k2, k3 all squared, psi3 trimmed trivially satisfies the MLT. So all rational functions with poles only occurring when k1 plus k2 plus k3 equals 0 are admissible. Hence, we can now construct psi3 trimmed for each alpha, which are consistent with manifestly local interactions. So now we can construct the full wave function coefficients by multiplying the tensor structure encapsulated by the spinor helicity variable with a solution to the MLT, with the symmetries of the MLT solution fixed by the symmetries of the tensor structure. We can then use standard techniques to convert these to bispectra, for which examples are given from equations 15 to 17. Remember that when we convert wave function coefficients to correlators, we divide by 3 factors of psi2, which scales as 1 over the power spectrum, so k cubed, which is where the factor of 1 over k1, k2, k3 comes from. For brevity, I've not included the bispectra for alpha equals 2 and alpha equals 4, but one can see from the example of alpha equals 6 that to go from a plus 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 configuration to plus plus minus, one just has to flip the sign of the k3 momentum and do similar operations for other helicity configurations. The order of the kt pole, p, for the bispectrum corresponds to the number of derivatives in the EFT of inflation interaction which generates it. The above structures are some of the most general graviton bispectra coming from free building block operators in the EFT inflation to all orders and derivatives, or equivalently to all orders in P. Compared to the general Lagrangian containing type 2 operators, one can write resulting bispectra to take a very compact form, and this is a clear demonstration of the bootstrap's power to circumvent cumbersome Lagrangians and go straight to the real world observables. So to summarize, in this soon to be uploaded paper on arXiv, we have worked in perturbation theory, and from this we have derived all three-level Graviton Bispectra in the EFT inflation to all orders and derivatives. This is actually the first time it has been shown that the quadratic and cubic action for massless gravitons that appears in addition to the Einstein-Hilbert part can be derived by considering covariant operators constructed out of the extrinsic curvature alone. This could also have repercussions for scalar non-Gaussianities. This classifies the possible Graviton bispectra for a large class of single field inflationary models, and hence gives observers an idea of what to look for in the future. But to do this, we use Lagrangians in a bootstrap. So I lied, we actually used both bulk and bootstrap tools. Future work involves reproducing these results in a fully bootstrappy way using consistency relations, i.e. soft theorems to subleading order. Given the previous point, it would be very interesting to construct mixed correlators and especially scalar correlators. Writing down the general EFT inflation action and doing this computation will not be very efficient, so one will need to develop bootstrap tools to construct these correlators. More ambitiously, one might expect to constrain bispectra by demanding consistency of higher point functions, such as the trispectrum. As discussed in Harry's and Gordon's talks, the cosmological optical theorem could be a tool to yield constraints on bispectra in this way. Thank you for listening, and I look forward to the upcoming discussions.